All right, everybody. Thank you all so much for being here. We're going to get started here today. So just kind of a quick overview about everything. So today's the 16th. So basically we have Lab 5, which is going to be due Monday night at midnight. Grade Scope will be open till Wednesday, so you can finish that up. So there's Lab 5, and then next week we're only going to have our final exam review. I figure we're going to just do it on Tuesday next week, and then probably Thursday of next week we're just not going to meet. I just don't think we need to. I'll send out a Canvas announcement next week, kind of formalizing that, putting it on paper and all. But all the same, so I think how it's going to play is that we'll have Lab 5 due Monday at midnight, we'll have our final exam review on Tuesday, and then we just won't meet Thursday. And that's going to be, our final exam is going to be on the 28th of April. Again, it will be a final exam, fully cumulative, it will be all online, and it will be open all day on the 28th, so you can take it at any point during the day. And I want to reemphasize that if the 28th is, if you're slammed, if it's a really busy time and you really just aren't going to be performant because you have to take multiple exams in the same day or something like that, just reach out, let me know what's going on. I'm pretty amenable overall to accommodating that, so don't want anyone to feel like they just have to, grind it out. Definitely reach out to me and let me know if April 28th for our final is going to be a conflict of some kind. So, but other than that, that's kind of the, kind of the rest of the semester right there. We really are in the home stretch here. Now, we're going to aim to have our exam review on Tuesday, April 21st. And I will have our exam 2s graded and returned to y'all before that point. And I will also make sure to, I think I already posted the Unit 9 supplement for studying, because the final exam is just going to be, for your study guide, just take the, first exam, the second exam, and the supplement study guides, combine them, and that's your final exam supplement. The final exam is going to be fully cumulative, so it's going to just cover a little of everything. I would say studying your past exams is going to be a valuable experience. I'm certainly going to ask you some stuff that weren't on those exams, but I'll almost certainly be circling back to some material that was. So if you understand specifically what's going on with your exams, I think that's going to be a big help, especially some of the juicier questions, like we had an assembly question on exam 2. I would not be all that surprised to see something like that, like a keystone element kind of show back up again. I will have all your outstanding grades will I'll probably just post them all tomorrow. I've almost finished grading your exams. I have a few stragglers I need to finish, so I can't post them until tomorrow. But I have graded the bulk of your exam too, so I'll be able to post them probably sometime tomorrow on Friday. Overall, I think they looked pretty solid. Definitely a significant improvement over exam 1, and I was pretty happy with the overall curve. So just want to let everybody know about that. Expect those to get released tomorrow. Just got to finish a few things up. If you're in my 304 class, oh, well, we're going to do our best. I think I got to do 304 next, so we're going to see how long that takes. But 311 is at least finished. There's about like 80 less people in 311, so it's a little bit easier. All right, so that's going to be that. And so yeah, I'm going to have every outstanding assignment returned back to you on Friday. So yeah, that's our final exam, and that's the outstanding work. That's kind of where we're at. So the last thing I wanted to really mention was just I wanted to remind everyone about course evaluations. I just got the email. Course evaluations have actually gone out there live. So please, please, please do not forget to do the course evaluations. Please don't forget to remind your peers and, bully your friends a little bit to, participate and do the course evals. Again, my two-tiered or my two incentives is I got the sappy one of genuinely y'all's feedback is the most important barometer I have for what's working, what's not, what I want to change, what needs to get fixed. And I really appreciate y'all's open and honest feedback. And the second thing is, again, if 80% of all of us submit the course evaluation, then we all get some extra credit. I think it's 10 points, probably in the assignments category. So it's basically like a free assignment that's 10 out of 0. Definitely a worthwhile goal, right? The extra credit's pretty nice. So they'll be open through this week and into next week. I don't know. I think they close sometime on the week of the 27th. I'll have to look again to see exactly when that date is. But all the same, that's going to be that. So please do the course evals. You'll see updates from me over the next couple of days about what our numbers are. And that's really it. I mean, one unrelated thing, but in case y'all weren't aware, there is a special election happening in Virginia on the 21st. And if you haven't voted already, I would highly encourage you to go vote and participate. It's important. If you're curious about my take, please, I would be more than happy to talk about it. I won't use the bully pulpit here to put out one view or the other, but I do always want to encourage democratic participation. So there is a special election April 21st, and I highly encourage you to vote in it. You can vote by mail. I think it might be a little late for that, but you can vote early. You can vote on the 21st, and I highly encourage you to do so. So yeah, there's that. And I think that's really all I have for my ranting and raving. So that's gonna, where did it go? Oh, it went there. So that's gonna really be it for that. So now what I wanna do is I kinda just wanna take today, and today's gonna be another free-form day, all right? Today's gonna be similar to Tuesday, but totally different topic, and a little tighter. So basically what I want to talk today about is the Game Boy, the original Game Boy developed back in the 1980s, and I just want to chit-chat about this a little bit, and I specifically want to talk about this in the context of the LC3, because on the LC3, we learned about a relatively simple von Neumann architecture machine, right? We talked about how the LC3 implements the instruction cycle, how it's able to, load instructions, execute them, and then kind of do amounts of meaningful work, right? We did our labs, and they're mostly just kind of summing numeric values, but we started to see, we have text I/O, right? That's what Lab 5's all about. Is reading in data, processing that data, and then outputting that data. And so we were really drilling down into the basics. And so while a lot of these core principles still apply to the modern computer systems that we all use today, the level of complexity between the LC3 and the M2 Apple Silicon chip in my MacBook Air is huge, right? Grand Canyon-esque size of a scope there. And so what I really like about the Game Boy is that it's old. It would be considered outdated on a technical level, but the Game Boy is a portable game console that was incredibly influential, and which I think complexity-wise is a pretty reasonable next step when going from the LC3 to something else, right? There's more complexity on the Game Boy than the LC3, but not so much that it's totally irrecognizable, right? I think there's a lot of touchstones and a lot of connective tissue, and I think that it's a kind of the next leap in complexity of where you'd want to go if you wanted to keep thinking about hardware. And the reason I think it's worth to keep thinking about hardware is because on the LC3, we can do stuff, but we are kind of limited to just, we've been doing number summations, right? And almost anything can do that. I can write a Python program to do that, right? It's a solved set of issues. But what I really like about something like the Game Boy is that its development, yes, but it's also the games that are produced for this system very influential, very popular, good, one might even argue. Like, the Game Boy has enough complexity on its hardware scope that you can make really meaningful pieces of code, right? You can make programs that are rich games, right? Games that are powerful, that are influential, that are interesting. And I think it's really I think it's just really compelling to show not just like, oh, this is how the von Neumann architecture works on the LC3, but like, this is a commercial-ass product that launched and also was incredibly influential, right? So we can take our knowledge of like the von Neumann architecture and apply it to a device that we can create really unique and meaningful and interesting programs with. And learning assembly, learning about hardware design is kind of foundational to programming and developing for this system. And yeah, this is retro, this is vintage, but I do think it's just like important to kind of make that connection of, well, it's not just that this is some abstract academic thing, right? This is something that you can apply to a real-world device and make something that's deeply influential. And I also think that the Game Boy and systems like it, of its vintage, of its era, I think you're going to see more and more popularity. I think you're going to see its popularity increase over time in the next couple of years. I think video games are a massive I want to say market, which is true, but like it's a cultural thing, right? The idea of video games as a pastime, as a hobby, as a thing that you are passionate about has really exploded in no small part because of the Game Boy over the past 25, 30 years, and it's not going away. But one thing that is going away in video games is the continual advancement of graphic performance. We've kind of peaked out. Back in the 2000s, into the 2010s, 90s, 2000s, early 2010s, the idea is each new generation of game consoles, each new couple of years would bring massive graphical improvements to your video games, adding fidelity, and this would add new capabilities. You could do new things with this new tech. And we've kind of hit a bit of a ceiling on that, right? Video game graphics technically improve, but we're not getting huge benefits out of them at this point. And they do have incredibly high development costs. So is your studio going to spend millions, tens of millions of dollars rendering each individual hair on Mario's fucking head? Is that really worth the effort and the money? And sure, if you're Nintendo, it might be, but I think we're going to start to see, especially for indie developers, a larger and larger push towards design under constraint, a focus on games that the gameplay mechanics, the hook, the story, really take center stage over the graphics or the other technical elements of the game. And I think development for the Game Boy, because of its restricted hardware, is I think that's a very useful tool. I think people still develop games for this thing, even if they're not sold commercially. And I think even if, the next game that goes viral isn't necessarily going to be a Game Boy game, I think that not only is it an interesting programming exercise, but I also think in terms of game development, it's an interesting exercise to build systems under constraint, to really have to focus on story or story or mechanics as opposed to just pure graphical fidelity. And so I think it's worthwhile for both of those reasons to really investigate this device, how it works, and how we can kind of map our knowledge from the LC3 onto something like this. And I would also say, if you're interested in hardware, like the very complex, very cutting edge, very modern stuff, having this as an intermediary, going from the LC3 to an 80s machine to maybe the 2000s into the modern day is kind of, I think, a series of stepping stones that can get you there. Just plugging your nose and jumping right into the tail end of the most modern, most complex stuff is very overwhelming. So, pretext and all of that yapping aside, let's break down a little bit about what this thing is, what it's capable of doing, and let's talk a little bit about how it looks in hardware. Okay, so the first thing I want to do is I get it. Okay, hardware. So I have technical documentation here, but I'm on Wikipedia, so whatever. Basically, it's got a custom CPU that runs at just over 4 megahertz. So not very fast, right? 4 megahertz is quite slow when we think of, the fact that most of our processors these days are running at, 1 or 2 gigahertz. Well, 1 or 2, 2 or 3. Somewhere between 2.5 and 3, really. But all the same, even though this is several orders of magnitude slower, the thing I like about the Game Boy is that you don't really need to you can do enough with 4 megahertz. Pokemon was developed for this system with 4 megahertz, and they made it work. And they made it work well enough that it took over the world. So clearly 4 megahertz is enough to make something compelling, right? And so I just like focusing in on that. And the other thing about something like 4 megahertz is that, when we start to build complexity, you need to care. When you're just working on these more super modern machines, you just throw everything you can at it and trust the hardware can work its way through. When you're working with only 4 megahertz, you gotta think about how performant is your code, right? You actually have to consider these factors. Anyway, so it's got a 4 megahertz processor and it has a black and white screen, but really what I want to do is I want to start breaking down the technical aspects. And so in order to do that, turns out there is a lot of documentation for this system available online. And not just like copied and pasted, photocopied documentation from the 80s and 90s. Like, people have gone and developed modern tools, modern documentation for this system. Hell, people have created new assembly languages. The underlying machine code is obviously identical to what the hardware produced, but like, people create their own assemblers and own their own assembly dialects that will assemble into the machine code needed to run on the Game Boy. But like, people have built all this up because they're like, well, I could do it conveniently, I could do this easily, and I don't have to worry about Nintendo copyright striking me or taking all my work down, right? Because you built it yourself. And so we have documentation, we have the Game Boy development system, and there's just a lot of other stuff going on here. So I want to start by looking at some of the hardware. And so the first thing I want to do is just kind of break down the memory map a little bit. And again, we're just kind of poke around a little bit, just see some of the different pieces of hardware. And really, my goal here is to kind of make connections to the LC3 to show that there are differences, but that we have some amount of commonality or some kind of understanding that we can make heads or tails of this in a way we probably would have a lot harder time doing, in January. So does that? Yeah, it does. So, similar to the LC3, actually, the Game Boy has a 16-bit address bus, meaning that the memory map is 16 bits. So 2 to the 16 memory locations on the Game Boy, just like the LC3. Now, the LC3, most of that memory map, most of those addresses are actually mapped or associated with like storage locations, like memory. But we do have the I/O page on the LC3 that lasts like 256 storage locations in memory that aren't actually, those addresses aren't actually associated with like a memory location. They're associated with I/O registers so that we can do I/O stuff using our standard data movement CPU instructions and keep things simple. The Game Boy takes this idea of, hey, certain memory addresses don't necessarily map to physical memory, but it's expanded a good amount, all right? So let's just kind of break this down. So we have the start of the memory map, right, from just hex 0000 to 3FFF. We are just given, right, 16 kilobytes of ROM. So basically, this 16K is just a ROM chip that is attached to the actual Game Boy cartridge, which, do we have? Okay, so basically the way the Game Boy works, for those unfamiliar, do we have another good picture? No. Okay, cool. Be really nice if we had a back shot. Okay, basically the way it works is you have your console and you have your cartridge and you smack this cartridge into the console. So the cartridge itself contains a number of different chips, including ROM, your read-only memory, your game code, right? This is the late 80s, early 90s, so there's no internal storage on the Game Boy. Pretty much game cartridges are going to store almost all of the data specific to your individual game, right? So basically the memory map, the first 16K are just connected to a 16K block of read-only memory that you read directly off the cartridge. The next 16K, so hex 4000 to 7FFF, is another bank of ROM, right? So it's another 16K of read-only memory. And this right here, these two banks, so 32 kilobytes, is all of the read-only memory that's mapped onto the Game Boy. So in theory, the Game Boy can only work with 32 kilobytes of read-only memory, and it can't use any more. So your game basically has to fit inside of 32K, which is not a very large amount of space. So that's how it's originally set up, but the issue is that, well, that's not a lot of space, particularly once you start putting graphical elements into your read-only memory, right? Graphics tend to take up more space than game code. And so game developers wanted more space to do more things with their games. And so this second chunk or bank of ROM, of read-only memory, is actually switchable. So the memory map for the Game Boy only has 32 kilobytes mapped out for read-only memory, right? So there's only 32K of addresses available to read data from your read-only memory on the cartridge. But the lower bank, the lower 16K bank, is switchable. So you might have a game that has 4 ROM banks. The top ROM bank, the 00 bank, will always be connected into the Game Boy, will always be readable by the Game Boy at any point in time. The other 3 banks, you can do something called basically bank swapping. You can basically say which bank is currently loaded in to these addresses. And so if you have bank 1 swapped in, then addresses 4000 to 7FFF will be associated with the read-only memory of bank 1. And so if you read data out, you'll get the data out of bank 1. But you can switch banks, so you can swap out the bank 1 with, say, bank 3. And then the addresses from 4000 to 7FFF are mapped to the data values in ROM bank 3. So while you can only ever access bank 0 and one other bank at the same time, you are able to switch between banks so that you can have a larger game. And when you think about a lot of different game design, the Game Boy screen is only but so big. And the way the Game Boy renders graphics, it's a pixel-based system. We're not looking like, the perspective is always top-down. Or sometimes it's like a movie perspective. You're not ever really playing games that are played from like a POV perspective with like a horizon and like draw distance. So you can get away with compartmentalizing. You really often only are looking at a very small subset of the world just based on the screen of the Game Boy, based on the graphical limitations of the screen. You're not going to deal with draw distance. You're not going to deal with, there's fog everywhere and it just looks kind of bad. You're looking either top down or like a movie projection looking to the side. And you're only ever looking at a small amount of the world. And because of that, you're only ever going to occupy a small amount of the world. So you can have a very large world and have each, say, part of the world or each town in the world in its own ROM bank. And when you go from one town to the next, you just swap banks. And that should work fine because you can only ever be in one town at a time. You couldn't see multiple towns at once because that's just not how the visualization of anything really is set up, right? That's just not the design language of these games. And so that is kind of the solution to get more memory, even though the memory map can't be expanded or grown, right? And the thing is that this was something that kind of happened after the Game Boy was released. Because these ROM banks are placed inside of the cartridges themselves rather than in the Game Boy system, you can just upgrade the cartridge. You can just have, oh, well, it's now 1992, and so we made a new type of cartridge that has multiple banks you can swap out. Do you need to change anything about the Game Boy hardware? No. Which is really convenient because you just sold a few, million Game Boys across, Japan, the United States, and everywhere else in the world, and telling everybody, hey, could you, buy another one? Yeah, good luck. Good luck with that. But telling people, hey, every time you buy a game, you gotta buy a new cartridge. And it turns out newer games can just use newer cartridges. From the consumer's perspective, yeah, just buy a new game. They don't need to realize that there's actually more read-only memory in the new game they just bought that their Game Boy can utilize. So that's nice and that's convenient. So anyway, 32K of read-only memory, that's going to be game code, that's going to be graphical assets, that sort of stuff, audio data, and that is going to be the top of the memory map, and again, the lower ROM bank we can swap out. So we can stash more data than we can directly map to, the Game Boy and the processor and all that. Processor can only access 2 ROM banks at a time, but we can have more in there and swap them around. And so it's worth noting that the next chunk of memory, so we have 8 kilobytes of video RAM, or VRAM. So we have 8K of video RAM. So pretty much all of our graphic processing, sprites, all that's going to fit in 8 kilobytes. Now we do have a map for another 8K, but this is external RAM. So your cartridge would have to have a chip that provides this 8K of RAM, and if that cartridge has this chip, you can access that 8 kilobytes of memory from addresses A000 to BFFF. But again, only if your cartridge actually has it. And odds are your cartridge won't, because, well, you gotta sell these things and make a profit, right? And the more chips that you put in your cartridge, the pricier it's going to be to make that cartridge. So you very rarely see this external RAM get used, right? Especially not from commercial games of the era. I think there might be a handful that use them because the devs were like, hey boss, so I'm really sorry, it's gonna fuck up your margins, but we need that. So we actually need that. Because if we don't have that, the game's not going to work, and then we can't sell any copies at any amount of money. And your boss is going to be very upset at you, but it's the 90s, and your boss isn't going to understand code at all. So once they're done chewing you out, they're going to say, I guess we need to do it, and they're going to just suck it up and pay for it anyway. But, all the same, that's where that comes from. And then from C000 to DFFF, we have 8K of work RAM. So WRAM, work RAM, you can think of as your main memory, your more traditional main memory, right? This is where we, just kind of load data and then modify it and then restore it. So the work RAM is going to be where you have a lot of the calculations about what's going on at any given point in your game, all right? And yeah, that's the bulk of it. We're not going to worry about Game Boy Color mode. We're just going to push that aside. So here's kind of the funny thing about this. So basically what this is saying is that the Game Boy has this kind of memory map, sure, but the first 32 kilobytes are all read in from a chip on the cartridge. It's not actually part of the Game Boy. And so the game, and then this 8K is also external, it's on the cartridge. So the Game Boy itself right? The actual Game Boy cartridge or the Game Boy system that you buy has 8K of video RAM and 8K of work RAM, and that's it. All right? So there's 8 kilobytes of memory for video processing and 8 kilobytes of memory for just general data processing. That's not very much. All right? And the funny thing is that from addresses E000 to FDFF, so basically the rest of the memory map effectively, this is echo RAM. So it's a mirror of C000 to DFF. So you might be wondering, why does the memory map exist in this way? Why does it mirror higher addresses, right? Why doesn't it do something useful, right? And is there any use to having echo RAM? Is there any use to having addresses that are effectively mapped to the same memory locations as other memory addresses in the memory map? The answer is no. There's really no reason for this, other than echo RAM is kind of designed in a way just as kind of a consequence of memory being expensive. Nintendo built a system with 8K video RAM and 8K work RAM, and the memory map is 2 to the 16 because memory addresses are 16 bits. And 16 bits is a sane number. 8 bits is too small for memory addresses because that's only 256 storage locations. Can't do that. And, well, why have 12 or 13 bits? That's not a power of 2. That's annoying. Who wants to fucking deal with that? So you can just have a 16-bit address and realize that the memory map is actually larger than the memory you're going to be putting into this system. And that's ultimately what echo RAM is. It's just kind of a consequence of, hey, well, we didn't have anything to put in these addresses, so they're just kind of wired back up to the circuit in a way that it just mirrors work RAM. Now, there's a note here saying that Nintendo says don't touch this. Basically, it's echoing these higher addresses, so just use these higher addresses. Don't use echo RAM. And Nintendo, I think, does this because, well, what if they want to upgrade the system, right? What if they say, oh, it's Game Boy 2.0 and it's backwards compatible, but we put more RAM in there that a newer game might use. Something like that, right? Nintendo's like, hey, this is undefined. This behavior might change later, so don't touch it. It works a certain way because that's how we built the thing, but don't touch it, is basically the demand. And then that's really kind of it. I don't need to get into object attribute memory. There's some unusable addresses that Nintendo also says keep out. Not really sure what that's mapped up to, but we already have all of our memory mapped into the memory map. So the only thing left are the I/O registers. Similar to the LC3, the Game Boy uses memory mapped I/O instead of having specific instructions for I/O interactions. So memory mapped I/O is another commonality between those two systems. High RAM is basically your L1 cache. That's effectively what it is. It's not quite the same thing. I think it's a lot more programmer controlled than L1 cache typically is, but that's the idea. High RAM, these addresses are meant to be very, very speedy, very fast, very right next to the processor. And then there's an interrupt enabled bit at the last address in the memory space. All right, so it supports interrupts as well. Interrupts are a lot more important on the Game Boy, but we don't need to dive into those right away. Now, that is kind of the full memory map. And what's this? Oh yeah, I/O devices. Huh. Look, there's a lot of documentation in here. I'm not gonna go through all of this necessarily, but it's in here. This has been extensively documented. And so the reason I like something like the reason I like something like the Game Boy is that it will teach you quite a lot about a piece of hardware that was complex enough that it was just a commercial product. You know what I mean? It's not designed, the LC3 is designed to be a learning tool. And so it will make changes, like for example, the LC3 is word addressable, and everything is the size of a word, which is 16 bits, right? Storage locations are 16 bits, registers are 16, everything is 16 bits. Basically, nothing does that. All right, like nothing uses word size for memory. Pretty much everything is byte addressable. Pretty much every modern system and pretty much every system going back to at least the 70s is byte addressable. Once you get to the 50s and 60s, when we really have no fucking clue what's going on and we're really just innovating, yeah, sure. But like 70s and onwards, everything is just byte addressable. And that's one of those examples of a change that the LC3 makes for academic reasons. I think it being word addressable makes it make more sense when you're learning about it for the first time, but byte addressability is just the much more standard practice, right? And so this is byte addressable, right? Each memory address is associated with a single byte or 8 bits of data as opposed to the LC3 16. So even though the memory map is the same size as the LC3's, the memory map on the Game Boy at its maximum can only store half the data of the LC3, right? Because each address is connected to 8 bits of storage, not 16. Yeah, not everything's connected to stuff, and I don't know what the actual storage capacity is when you do math, but like just in pure, broad, general sense, right? An address is connected to 8 bits instead of 16 bits, that's half your capacity right there, all right? So anyway, I just think that that is interesting. So that's the main thing, right, I wanted to kind of note about that. I'll simply note that the I/O registers, there are a lot of things that can demand interruption, and I just want to point these out because I think these are a better example of like interrupts, which we only kind of skimmed. So basically, the joypad can have can trigger an wait a minute. These are I/O devices. Where are the interrupts? Is it not? Oh, it's all the way over here. Okay, we're going to ignore that. These are just the I/O devices. I misread this, sorry. But basically, just like there's a lot of different I/O devices on the Game Boy. So for example, the joypad, right? So just the actual input, right? Instead of your I/O device being a keyboard, the Game Boy is a total of 8 buttons. You have a 4-direction directional pad, you have A button, the B button, the start button, select button. So that's 8 different individual buttons. And so this register here at FFOO, so basically it's byte addressable, so it's a single byte, 8 bits, and each bit is connected to one of the 8 input buttons on the Game Boy. So if a single button or multiple buttons are pressed, then the associating bits in this register are set to a 1, and when they're released, they're set to a 0. So you can, to try and get user input, just read the value of this register at any point, and, well, if there's 1s, that tells you certain buttons are being pressed, all right? If you're not going to do interrupts, then this is probably polling. You're probably polling this. The difference between polling that we saw on the LC3 and polling on the Game Boy here is that the LC3 is constantly polling the I/O device until it's ready and not doing anything else. Whereas a game would probably do all of the stuff it needs to do. It would probably have like a game loop. And like basically each frame, so to speak, it would render the frame, it would check the state of the game, and it would also check the state of the joypad. So it's not necessarily a performance hit, but rather it would be like, hey, we check the joypad once every frame. So if you're pressing and releasing a button faster than a single frame, we might miss it. We're just gonna bank the fact that, well, we have more frames than your finger is fast. You know, if you're playing a game at 30 frames a second, you're going to be checking the joypad once every 30th of a second. And the odds that you're going to tap and untap a button within a 30th of a second, no, you're not. Unless you're doing some weird speedrunning shit, in which case you'll probably find out, oh shit, it doesn't like my input sometimes, I'm too fast. And then you might realize that. But like short of breaking, but if you're just releasing a game to the general public, you're not testing for that. So that's how polling can be used in a way that isn't really damaging to performance. It's just, hey, every 30th of a second, I gotta render a frame and do a bunch of other stuff. And one of the other things can just be check the input. And if I just do it once, but I do it once every 30th of a second, then I'm sure I'll be fine. I'm sure that's often enough that I'll just see any state changes, And that's a choice you make as a developer. If you're running your game at 15 frames a second, at 10 frames a second, then, well, is that fast enough? Is it not? Well, there's no one to tell you. Play test it. And if it's not fast enough, that might be a problem because it might be too late to change it. But the Game Boy really forces you to engage with everything, right? You have to think about pretty much every element of hardware and software, which I'm glad isn't my job, but is, from a computer science perspective, I think very interesting in a way of, I'm working with this super high-level third-party library and it does most of the work. I'm just trying to figure out how to wrangle that thing to do what I needed to do to, get paid and go home. This is a bit more of an art, if you will. And there's a bunch of other stuff, but I think the joypad is enough. But just that there's a lot more I/O devices. We have audio systems. We have the whole damn display. And the display has a lot of different parts to it that you've got to be able to control. You have the IR port. That's not for instruction register. That's for infrared. So this is only on the Game Boy Color. But the Game Boy Color, which... Do we have a good picture? Bro. No, we don't. Hang on. Just give me some really fuck ugly picture. Okay, look at that. Apologies to whoever. Oh my, can I just open an image? I don't want to view the file on your website. Whatever. With respect to whoever took the photo, anyway, that little black cutout in the bottom right of the console right there, that's just an IR beam. And the idea was that you could just stick it right up next to another Game Boy and it would just blast infrared and they'd talk to each other that way. Nobody used it, for the record. Like 5 games actually bothered to take it. It's like, it's cool in theory. When I say right next to each other and it'd work half the time, I mean, you are just kind of blinking lights at each other, and so each pulse of light is a bit. You can lose bits of information pretty easy, right? If you don't notice one of the flashes, it could bork the whole thing. So this wasn't used very much, and it was finicky when they did, but it was a cool idea. And that's also another example of where the cartridge goes, right? You just slot it right in the back. And the nice thing is that, yeah, that's like sort of external, but unlike, so here's the thing, a lot of times when you think of like I/O in the modern sense, like you're plugging in like a flash drive into like a USB stick. And so, the USB port is what's connected to the computer. And so that's kind of like a something in the middle, right? The CPU talks to the USB controller stuff, and the USB controller stuff talks to whatever you just plugged in. And so if your CPU wants to talk to your, say, flash drive, both of them have got to communicate through a third party, an intermediary, the USB controller. But with the Game Boy, when you plug in a cartridge, you are plugging that directly into the system. It is like you are wiring it into the system bus. There's no third-party intermediary communicating between the two of you. When you plug in a game cartridge, that cartridge is now like effectively part of the Game Boy, right? That's how it shows up directly in the memory map, is that you're connecting it directly to the main system bus, right? So the CPU can talk to all the chips on that cartridge directly, in a way where when you plug in a USB stick, you gotta talk to the USB controller, and the USB controller is what talks to your flash drive, and you gotta communicate between a middleman. So yeah. there's a lot of reasons why you don't want to do it that way, but for something like the Game Boy, where it's like, yeah, the cartridge is effectively part of the system, well, that makes sense. Because, well, you don't have to worry about security issues or anything like that. There's no memory, there's no persistent storage on the Game Boy itself. There's no way to hack it. This thing doesn't go online, doesn't store any personal information. And also, Nintendo has to approve of every cartridge that is manufactured and sold. So Nintendo's not going to let you sell a game that doesn't have stuff Nintendo doesn't like on it. So they don't got to worry. You know, they connect the cartridge right up to the system bus. It'll be safe. That's not a guarantee you can normally have. But yeah, anyway. Copy protection and, okay, not relevant, but very funny. It didn't work, but basically Nintendo's whole shtick was like, hey, how do we prevent third-party people from making games for this? When you were allowed to be third-party, you just had to pay Nintendo. And then Nintendo had to approve it. And if Nintendo didn't like your shit, they would just say, yeah, get bent, we don't care. You needed the official Nintendo seal of approval. Now, this sounds very Apple, kind of just doing it for the sake of control, and it's part of that. But they did have a justification. It's worth noting that video games really popped off in the United States in the late 1970s, early 1980s. The invention of Pong in 77, I mean, that shit went gangbusters. People loved it. And like, it's Pong. Sometimes I think it's a little hard for us to appreciate that because it is just so primitive. You can see why it was fun, but I think it can be hard to appreciate how much of a cultural phenomenon it was. People would just sit for hours playing Pong because it was the 70s, y'all. It was, you know, when are you gonna do, drive somewhere? There's no fucking oil. Oh, surprise, surprise. Turns out, don't fuck, oh, don't. Yikes, anyway, sorry, I'm getting flashbacks to modernity. But, so that was kind of the state of things in the late 70s, early 80s. But the problem is that just there were a lot of video game consoles that emerged. There was a lot of games getting made for them. The quality control was just not there. So companies kept making more and more shittier and shittier games. And then eventually you have the video game crash of 1983. I'm going to say 3. Basically, the catalyst is historically attributed to, there's a lot of factors, but the big story was Atari produced the game E.T., which was a movie tie-in for the movie. The movie was really good. The video game is widely considered to be one of the worst games ever made, and just a historical, fucking awful experience. All right, like yikes. All right, everyone despised this. And this was actually so bad, like Atari had just assumed that they were gonna sell a lot because of the movie. And so they made millions of cartridges for E.T. And it went out, a word got around pretty quick. And this is like pre-internet era. So like trade magazines and people figured out pretty quick that this was a steaming pile of shit and nobody should buy it. It got so bad that Atari took entire like shipping crates, like shipping containers worth of game cartridges, and just dumped them in the middle of the desert out in New Mexico, a little outside of Albuquerque. Look, if y'all have ever seen Breaking Bad or Better Call Saul, there will be scenes when they're out in New Mexico and it's just desert for literally miles, there's no civilization. They're not exaggerating. That is the vibe. It does not take long to drive outside of one of the 2 major cities in that state and just be in such unknowing wilderness that, it's civilization is just not there. And so Atari just took a couple of shipping containers and just dumped them in a hole in the ground because that was cheaper than dealing with them in any other way. And there was a rumor for a long time, but within the past 10 years, a couple of people found it. I think they did look through old Atari business records. When you go out of business 4 or 5 times, the old files get churned around, and they figured it out, and they started digging, and all of a sudden, they're just digging in the old New Mexico dirt, and they're like, E.T. Don't think that's a natural plant or anything. So anyway, I'm ranting, but the moral of the story is that this is so cataclysmic, and video games are seen as a bloated industry. They're seen as a fad. The entire market collapses. Stores won't sell video games because stores think that this is just a way to lose money. And if you're a small business, yeah, it makes sense. You know, you've got a lot of different video game competitors, and they're all selling games, and maybe you bought into the whole ET hype. You don't know what video games are. You know, you're in your 40s or 50s, and this is some kid's thing. You have no idea. You just think, it's popular, it'll sell, and now you're out thousands of dollars because, no, it didn't. So nobody wants to sell video games. The market pretty much dries up and dies. America, no video games really in 84, 85. But Nintendo over in Japan has their Famicom game system. It sells a lot. They would really like to break into the US market. But they know they can't sell a video game console in America. No one will ever put it on the shelves. So the geniuses at Nintendo said, well, it's not a video game console. It's an entertainment system. So if you're ever wondering why it's called the Nintendo Entertainment System, that's why. Video games were a toxic commodity in the 80s. And so they're like, it's an entertainment system. It's a toy. It's not a computer. It's a toy. Don't sell it next to the Apple II. Sell it next to Hot Wheels. And that worked. Worked very well. Now, if you've ever wondered why video gaming has historically been so male-dominated, well, it's because we're fucking weird and we gender the toy aisle very explicitly. And so in the 80s, if you wanted to sell a toy in the United States, you had to pick a gender. And they picked boy. And so all the marketing is marketed towards boys because it's not really the Nintendo Entertainment System, but that's where that comes from, right? Because you had to pick a gender to market to sell your toy. And they're like, okay, do we put it next to Barbie or Hot Wheels? And they picked one. And that's the small domino that leads to the big domino that's like, I don't know. I used to say Gamergate, but Gamergate's the small domino that led to, like, fascism in America. So, like, wild fucking choices. But I'm sorry, the connective tissue is there, it's real, and I think it's worth pointing out more. But anyway, if you've ever wondered where a lot of those seeds come from, it's a marketing gimmick for Nintendo to get into the American market. And I think that's fascinating. Is that particularly related to computing? No, but whatever. The things you end up learning about the world when you're just trying to figure out how code works. Anyway. Other thing I wanted to mention here, while I'm just kind of going off, is the CPU instructions, all right? Now, the LC3 had 15 CPU instructions with like room for a 16th. The Game Boy has a lot more, all right? The Game Boy has a lot of CPU instructions, all right? I don't know, it's like 64, I'm gonna just spitball and guess. But a lot of them are quite repetitive. But before I hit this up, I think there is a better view of this here. Okay, there is. Basically, let's talk registers. Let's talk general purpose registers. So on the LC3, we did a lot of our computational work. We had main memory, and then we would load data into a general purpose register, R0 through R7. We would manipulate data in the registers and store data back into memory when we're done. The Game Boy is quite similar. We have main memory in the form of our VRAM, or we can read data from the read-only memory. And we do have some general purpose registers that are near the processor for temporary storage to do data manipulation with. Now, these registers are 8-bit registers because it's a byte addressable machine, unlike the LC3's 16-bit registers. And we have 5 to 8, depending on how you count. So you have 8-bit registers B and C, and D and E. So that's 4 8-bit registers. The Game Boy is also nice, and it allows you to combine 2 8-bit registers into a single 16-bit register, which can be very important. Memory addresses, remember, are 16 bits. So if you need a memory address in a register, it won't fit. So you can just conveniently say, oh, I'm going to use register BC, which is really just you saying, I'm going to use register B for the first 8 bits and register C for the second 8 bits. But the Game Boy knows you're going to do this, so it just kind of lets you reference it as BC and just treats it as one 16-bit register. It's just a shortcut for convenience. So we've got BC and DE, which are 4 total, 2 each 8-bit registers that can be combined into 16-bit registers. You have H and L, which are another 2 set of 8-bit registers, but HL is usually used as a 16-bit register. It's usually used for memory addresses. You can modify just H or L. It's just not as common. You have a stack pointer and a program counter, right? So we have our program counter, which we're familiar with. You would imagine there's an instruction register in here too. But the instruction register is not something that you're ever going to write a CPU instruction to manipulate, so we don't need to include it in something like this type of documentation. The program counter, on the other hand, CPU instructions might modify, like a branch instruction, right, or a jump. That's going to update the value in the PC, so putting it here is more important. We do have our own custom register for the stack pointer. Instead of just R6, right, there is a register whose job is stack pointer, because everything's using the stack, so we just got a dedicated stack pointer. And then you have A and F. So A is an accumulator register, it's 8 bits, and F is your flag register. Nominally, you can use this as the 16-bit AF, but you're really not supposed to. It does not like when you do that. The F register is really meant to be a read-only register, because it stores flag information, kind of like the NZP codes on the LC3. That's all in an 8-bit register called F. And then A is just an 8-bit register, and it's where the results of a lot of CPU instructions are just kind of dumped in. And yeah, you've got your flags. You have a Z flag, which indicates if the last result was 0 or not. And unfortunately, instead of having positive or negative, you get a subtraction flag, a half carry flag, and a carry flag, which are very confusing, and I don't really want to get into them. But basically just showing NZP is one approach. This is a different approach. And this one's honestly more common. But again, the LC3, recognizing that this is goofy, decides, nah, we're trying to teach people. Let's go with NZP. That's a lot more naturally intuitive than, because subtraction and half carry have something to do with binary coded decimal, which is a thing IBM created in like the 60s, and it's a whole rat's nest to try and understand. You can, but there's a reason why the LC3 doesn't want to take all that baggage with it. All right, but similar flags, which are going to be used in similar ways to the NZP flags. And then just to kind of go through, you have your load instructions. So while this is a lot more instructions than the 3 we have on the LC3, I think a lot of them are, relatively speaking, use a lot of the same principles. Like for example, this LD R8 HL, you're basically going to take the 16-bit register HL, treat the value there as a memory address, go to that location of memory, find the data there, and then store that data into an 8-bit register that you specify. So that's basically like an LDR instruction on the LC3, but it's just written differently, right? This LD R16A basically says, hey, we're going to copy the value in register A into the byte pointed to by R16. So I don't actually think there are any store instructions here. There aren't. So basically, the load instructions are also your store instructions. They go both ways. They're bidirectional, which is fair, I guess. All right? That's really an assembler / design choice. totally fair game. Again, makes more sense the LC3 wants to be explicit about this, right? You have loads, you have stores. Whereas here, it's all loads, just what direction are you loading? Are you loading from memory to a register or from a register into memory? They just call all of that load. Okay, again, different, confusing, takes some time to get used to, but I think a little bit more intuitive, not intuitive, but a little bit more seeable when you have the foundation of like the LC3 instead of just being like, well, okay, load just kind of does everything, I guess, I could go through all of these, I don't want to, right? And also, you can move from a register into another register. So you can do register to register copying. It's convenient. Your arithmetic operations, you've got adds, you've got compares, you've got decrement and increment functions, you have subtraction functions, actually, which is nice. You'd imagine a subtraction is doing similar to what we have to do on the LC3, right? Where you're taking your positive 2's comp number, inverting it, adding 1, and then adding the 2. But that might be what that does. It's just abstracted away. Maybe that's just done in hardware. If you invoke the subtraction instruction, well, the CPU takes in the thing you're subtracting, takes that positive number, makes it negative, and then does the operation, right? Does the add. So I doubt the CPU does anything but add, but maybe the CPU, when given that instruction, will make one of your operands negative and then add them, effectively a subtraction, so you can just write a subtraction operation. I could probably, well, no, I don't know how that works. But yeah, so we have increment, decrement, some compares, some adds, add with carry, which I don't want to think about. You've got some 16-bit arithmetic instructions. You don't have many of them, but you have some. So you've got some adds, some subtracts, some increments, some decrements. You've got increment, decrement, and add for a 16-bit value. So this is really for memory addresses, right? You can add a 16-bit value to an address in the register HL. You can increment or decrement a value in a 16-bit register. So if you have a memory address in HL, you can just use one instruction to increment it, which if that, say, HL points to the start of an array or some type of data structure, might be convenient to just increment it each time you read the value, increment, look at the next value. Something like that. Your bitwise, you've got your ANDs, ORs, and your XORs. That's convenient. Yeah, cool. Some bit flag instructions. So, and then bit shift, we don't talk about on the LC3. It doesn't have a bit shift instruction, which is, I would say it's a shame, but the 16th instruction, the missing instruction, is a bit shift instruction, and it's for the computer engineers to implement themselves. I want to figure out a way to talk about it, but basically bit shifting is just if you've got an 8-bit value, just shift all the bits to the left or shift all the bits to the right, right? And sometimes you shift all the bits to the right and then you just copy the highest bit into the lowest location, like it wraps around. Sometimes you drop it and put a 0 or a 1 in the space that is now empty. All depends, and you can just read these to figure out what they all do. And then you have your subroutine calls, your unconditional and your conditional jumps, and your, returns. All right? I don't think, yeah. Miscellaneous, interrupt related, we don't need to talk about, although we do have a halt instruction, so go us. And they have instructions for the stack. Now, the reason they have specific stack instructions is because there's a specific stack pointer. So I would assume that the vast majority of CPU instructions can't modify the stack pointer. Only the stack pointer instructions can modify the stack pointer. So you're less likely to accidentally clobber your stack and mess that up. On the LC3, it's really easy to mistakenly modify the stack pointer when you're not doing a stack operation and break everything. We're not doing anything with the level of depth and complexity required to really have that happen. But that's why it's like this, all right? You have your own stack manipulation instructions because the stack pointer is its own separate thing, right? R6 is normally the stack pointer, but it can just be a general purpose register if you're not using the stack. Stack pointer is only the stack pointer on the Game Boy. And so yeah. And also it tells you how many CPU cycles it takes to execute each one of these instructions. So efficiency matters when you only have 4 kilohertz, or megahertz rather, it's definitely megahertz. But when your CPU is running at like 4 megahertz, you might have a lot to do with not a lot of processing time, especially if you're a video game where like frames and rendering, like it has to feel responsive, right? When you press the up arrow on like the gamepad, your player needs to move. If it takes a half a second for them to move, it's not a game anyone's going to want to play. So keeping track of how many CPU cycles each instruction takes so you can get a rough idea of like how many seconds all your operations will take is important, because you need to make sure it's fast enough that your game is still responsive. That if you're doing, say, 30 frames a second, it's not quite how it's measured on the Game Boy, but whatever. If you're doing 30 frames a second, you need to kind of measure, you need to pay attention to how many cycles it takes so that all the stuff you need to do in between each frame can actually be done in 1/30th of a second. So that's why that information is relevant here. Okay, cool. So I'm basically done, and I ranted about that more than I thought to, but hey, so fun fact. Oh, okay. What if IDK? Cool thing. I mentioned Pokemon. Gen 1 Pokemon's written all in assembly. All right, because it has to be. Because Game Boy games are all written in assembly. They're written on the metal for the hardware that is the Game Boy. And so the cool thing about assembly is that there's been a big disassembly project, right? When you assemble a piece of code, it's just a one-to-one association of the mnemonics, right, the actual assembly language, and the machine code, the ones and zeros. So it's a relatively easy process to undo, right? Just turn all the ones and zeros back into their assembly mnemonics. This works. The problem is that it's all just one big honking blob of code, and there's no comments, and while you can generate labels, they're not named, right? Label names are not part of the assembled product. They're just all math offsets. Now, when you disassemble, you can replace the offsets with labels, because you know where the offset's going to, so you can just put a label at that and use the label in the instruction. But like when we write code, nominally we're giving the labels, like names, all that's gone. So they're all generic. So you can disassemble it, but it takes a lot of effort to reverse engineer it and figure out, oh, what code does what and what goes where, and break it all up and make the labels make sense, add some comments. And there's been a very massive project on the Game Boy to do that. And so, turns out, hey, fuck, if the source code's right there, you can modify it. So I did. I liked playing, this is like half-baked and half-done, I kind of ran out of steam. Work, right? Anyway, basically, I wanted to play this game. I have a lot of nostalgia for it, because I am of that vintage. And, yeah, I'm not 6. There are some features that are missing that make it damn near unplayable. There's no running shoes, for example. Flash sucks as a move. There's no move deleter, so you have to give someone Flash and then abandon them forever. There are bugs and glitches that make the battle mechanics bad. There is a limited number of items. There are glitches aside, I added some moves to balance out the mechanics. So I did a lot of stuff, all right, in here. Again, it's a toy for boys. You weren't able to play as a girl until Crystal, so that's kind of at the end of Gen 2 before they were like, oh, wait. So I added that back in, just a lot of different individual pieces of stuff. And the one I wanted to find, I am just pulling my like old commit kit. Okay. You can actually go through some of the code here Okay, look, I wrote a bunch of code, and I commented it, and I don't remember how any of it works whatsoever. But basically, here's what I wanted to show. I want to go into workram, and I want to find that guy. Okay, cool. Huh? Did I close it? Yeah, shite. Huh. Strange. So, there we go. Cool. So, we can bring up this, all its chiptune glory. No, not that one. Hi, where's the other save file? Huh? Huh? Well, that might be a problem. Well, where does my save file go? Oh, there, okay. Panic averted. Alright, so basically I added a couple of features. I don't need to go in there. So one feature that I added that wasn't there previously is when you can press A on the environment and it'll ask if you want to use an HM move. Not a feature in the original Gen 1. You need to just open up the party, select the HM you want to use, and then activate it. So now I have it detecting what tile you're looking at, and if you have the badge and the Pokemon with the move, it will just bring up the screen when you tap A. It's kind of buggy, but it works good enough. So we can surf around, which is really nice, see the truck. This spawned so much conspiratorial thinking back in the day. And here's the big thing I wanted to show. In the original Gen 1, this is your bag. There is no organization, there is no sorting, you just have a bag. And the bag has a pretty limited amount of space. And the reason it's a limited amount of space is because there's not much memory, and each item takes 2 bytes to store. 1 byte is the item ID, pretty much identifying what the item is. The second byte is quantity, identifying how much of the item you have. Now, nominally, you're limited to 99 items here, but it's a byte, so it can go up to 256. It's not supposed to, but it can, all right? But at 2 bytes per item, and you have a very limited amount of random access memory to use, you're not gonna make the bag very big. And so if you wanna collect all the TMs, you don't have that much space for it. So there was no TM case in the original Gen 1, but I added one. And it renders the name of the TM, which it did not ever do. In Gen 1, you just have TM18. If you want to know what that is, you got to try and teach it to somebody, and then it'll display the name, and then you got to see if you want to do anything with it. Very cumbersome and annoying. So how work? I didn't want to use up all the space for RAM. I had the same constraint that everybody else did. But I remembered Gen 5 exists, and took some inspiration. So normally, every item requires 2 bytes to store, right? But I figured, hey, if I make TMs infinite, I make them always reusable, then I don't need to store a quantity, right? I can just store the ID. And also, TMs and HMs, they're the numeric values used to identify a TM or HM item. They're linear in like the memory layout. So basically, say like element 1 is TM1, element 2 is TM2, etc. So what I did is instead of storing each TM as a set of 2 bytes, I have a TM case which just uses individual bits. So a bit is set, meaning you have that TM, and a bit is not set, and you don't have that TM. So right now it only is just 2-bit set. So 55 TMs and HMs, that's 7 bytes for the whole TM case. And I'm kind of out of time because I didn't manage this, so y'all are good to pack up and go. But just to prove a point for those who want to see, I can open up the memory viewer on this thing. let's just back out really quick. I can see that, where is it? WTM case item is at D598. So I can actually go to D598 right down here. And I can set these bytes to FF. And then, oh gosh. That's too much, but whatever. So I basically just took the 7 bytes I allocated for this and I set all of it to FF, which is all ones. So now, if I open back up the TM case, we've got everything, because all the bits are set to 1. And we can see that it works, renders everything. And yeah, I'm pretty proud of this. Now the problem is that I can go past the cancel menu because the number of items in the bag is set by this value right here, and I don't remember what in hex the max number of TMs and HMs is, so I guessed with F5, and I guessed wrong. So I'm like basically you're telling the game you have more items in the bag than you actually have, and weird things happen. But anyways, what happens when you poke at memory directly. I also added some moves and some other things, but I decided to rant about the video game crash of 1983 instead, so c'est la vie. Anyway, thank you all so much for being here. I hope this was at least somewhat interesting. Thanks for being hostage all week to whatever I want to talk about. We'll be back here Tuesday to do a final exam review, and then that's it. Cheers, y'all. Home stretch. Have a good weekend, everybody.